So it's a pleasure to welcome second speaker of today, Martin Heirer from Imperial College. So Martin, if you're ready, please.
Mm-hmm. Okay, thanks a lot. Thank you very much for the invitation. It's a pleasure to, well, to speak here from London, to be virtually in India. So the work I want to talk about today, it's some recent work joined with Michele Cotti-Zelati, who is a associate professor here at Imperial as well. And so the original motivation for this work was the following. So imagine you take the 2D or maybe 3D Navier-Stokes equations driven by some quite regular Gaussian noise. Okay, so you just put some random forcing on the Navier-Stokes equations on a torus. So here, this is on the torus. And now we know, so with together with Jonathan Mattingly, about some time ago, 15 years ago, I guess by now, we proved that if the noise is sufficiently non-degenerate, and basically sufficiently non-degenerate here means that it shouldn't somehow sit on a subspace of functions that have smaller periodicity, then the evolution is ergodic. So what this means is that, you know, exponentially ergodic even. It means you can start with any initial condition. You run the system for a while. Because it's noisy, it's not going to just go down to zero, but it's going to approach some steady state. And this is true sort of for arbitrary Reynolds number, right? So this is also true for high Reynolds number. So it's not the case that you don't necessarily have a sort of one force, one solution principle, right? So the noise can be pretty strong. On the other hand, we know, and that was proven a little bit earlier by a number of people, so including Mattingly, Sinai, and and there were papers by Kuxin and Chirikian. So it's been known for a bit also that if the Reynolds number is small enough, and for the purpose of the talk here, small enough Reynolds number means, say, small forcing, then the system is exponentially ergodic without any sort of non-degeneracy condition, right? So of course, you know, your noise could just be zero. And then of course it's exponentially ergodic as well, because if you take the viscous Navier-Stokes equation, well, of course, if you start with anything, you're going to converge exponentially to zero. Now, you notice that there's one case here which is left out, which is the case in which the Reynolds number is large, but the noise is degenerate. Okay. And so the kind of situation, right? So the sort of situation that you should have in mind is take 2D Navier-Stokes on a torus. So say I identify these sides and I identify these two sides. But now you take you use a forcing which is actually periodic with, you know, this period here. So you take a forcing which is actually periodic with half the period. So whatever so not statistically, right? So it's actually kind of pathwise periodic with half the period. So whatever the forcing does here, it does exactly the same here, here, and here. And now you ask yourself the following question, which is, well, on the one hand, of course, if I start with an initial condition that is itself periodic with half the period, right, then that subspace is going to be invariant. Right? There's no reason to leave that subspace. And on the space of functions that are periodic with half the period, I'm going to say assume that your noise is actually non-degenerate. Right? So then you can apply the result we had with Jonathan, which tells you that there exists a unique invariant measure and it's exponentially ergodic, provided that you restrict yourself to that function space of functions that are periodic with half the period. Okay. now the question is, what happens if you start with an initial condition which is not periodic with the smaller period, right? So you start with an initial condition that has some kind of long wave number, so sort of low wave number kind of contribution, right? Some low frequency contribution. And okay, so now we won't answer this question because we don't know how to do it, and this seems to be very hard. And so what we tried to do is answer that question for a much, much simpler toy model, which still has pretty much the same kind of features as the situation that I just described. Okay? And the toy model in question is just the Lorenz system. Okay, so of course you all know the Lorenz system. So I just remind you what the ODE looks like. So it's a 3-dimensional ODE. It has similar features to the Navier-Stokes equation. And of course, it was originally introduced by Lorenz as a toy model for atmospheric convection. And so you see, it has sort of a similar structure in the sense that there's a linear part. So here you see this bit is linear. Here there's a linear bit which comes here. Here there's a linear bit here. Then there's a nonlinear term, which is this xy here and this minus xz here. And the nonlinear term preserves the L2 norm. So here L2 norm is really just, x squared plus y squared plus z squared. You see, if you apply the time derivative to that, well, here you get a term which is sort of minus xyz, and here you get a term which is plus xyz, and they cancel out. So in that sense, the nonlinearity is bilinear, just like in Navier-Stokes, and it preserves the energy just like in Navier-Stokes. And for this Lorenz system, well, if you fix, so these parameters sigma and beta, they are not super important. So we're just going to assume they're positive and fixed. You fix them once and for all. There are sort of standard values for the pictures that you tend to see online of the Lorenz attractor. It doesn't need to be these precise values. You just choose anything. The interesting parameter here is rho. And what happens is that if rho is less than 1, then this system sort of really behaves like Navier-Stokes without external forcing, in the sense that you can start with any initial condition. The origin is globally stable, so any solution just converges exponentially fast to the origin. Okay, so rho smaller than 1 is really a bit like Navier-Stokes. For rho bigger than 1, the origin becomes unstable, and then you have this strange attractor that, of course, you have all seen 100 times. The strange attractor actually doesn't occur for all possible values of positive rho. Then at some point when rho gets very large, there's sort of a limiting cycle which becomes stable again. But okay, there's a large range of rhos for which you have that strange attractor. But that's not what we're going to be interested in, right? So we are going to be interested in this as basically a toy model for Navier-Stokes. And so we actually use rho, we fix rho less than 1. Okay, so we are in the regime where the origin is actually globally stable. So there's no strange attractor for the deterministic system. And well, so I claim that this is sort of a toy model for the situation that I described before. And the situation I described before was kind of Navier-Stokes on a torus, which then ends up being forced with a forcing that has a period that's half the period of the torus. So what corresponds, so what's the analog here of the space of functions that are periodic with half the period? So it should be some linear space which is invariant for the dynamic. And here there is a linear space, subspace, which is invariant for the dynamic, which is the one where x equal y equals 0, right? Because if x equal y equals 0, then you see that the right-hand side here is 0, the right-hand side here is 0, and therefore x and y will remain 0 for all times. And then that term drops as well, and the equation for z is just a linear equation. Okay, so that's somehow the analog of the subspace of functions that are periodic with half the period. And so what we do is we add noise to this equation. And the noise term that we add is just some multiple of white noise. So this psi here is white noise. And we add the noise only to this Z component, right? So that's the analog of adding noise to Navier-Stokes, which is periodic with half the period. So in particular here, if I start with an initial condition where X and Y are 0, then that's still going to be invariant, right? Because the noise here acts only in the Z direction. And so the dynamic is just going to stay on the Z axis, and it's just going to perform an Ornstein-Uhlenbeck, right? So it's actually just going to be an Ornstein-Uhlenbeck there. And now the question is again, what about invariant measures and sort of, long time ergodicity? So how does this system behave for long times? So of course, if I start on the vertical axis, I stay on the vertical axis, this drops, I just have an Ornstein-Uhlenbeck process. Obviously, it's exponentially ergodic, nothing interesting to see there. So the interesting situation is the one where I start with an initial condition which is not on the vertical axis. Okay, so I start with an arbitrary initial condition which is not on the vertical axis. And then I ask myself, well, what's going to happen? Is the solution going to simply converge to the vertical axis for long times? And that would be the analog of sort of low Reynolds number, right? So sort of if you expect to have something like a 1 force 1 solution principle, that would mean the invariant measure has to be unique. I know that there is one that lives on the vertical axis, and therefore any initial condition should actually lead to a dynamic that converges to the vertical axis. Or on the contrary, does the vertical axis become unstable? And in that case, well, do you have a second or maybe third or whatever? What happens outside the vertical axis? Is there a sort of non-equilibrium steady state outside the vertical axis? And the theorem that we proved with Michele is that you actually have a transition depending on the value of alpha. Okay, so it's certainly not surprising that if alpha is very small, then this is essentially a perturbation of the deterministic system. And for the deterministic system, since I choose rho less than 1, we've already seen that there is this kind of 1 force 1 solution, but everything just converges to 0. And so if I add a little bit of noise, you can imagine that, well, sort of the origin stays somehow very stable. And so you actually, the vertical axis sort of remains stable and it attracts all solutions. And the more interesting case is that we show there's a critical value of alpha, so that for values larger than that critical value, well, there is actually the vertical axis becomes unstable. And so there is another steady state, which gives measure 0 to the vertical axis. And furthermore, that one's actually unique. So there's exactly 2 steady states. There's the one that lives on the vertical axis and the one that lives away from it. So let me just show you what a simulation looks like. So here, I fix all the parameters. A rho is less than 1, except for the intensity of the noise. And what I draw here is 2 different trajectories for 2 different values of alpha. So here you see the red trajectory here. All it does, it starts, so that's the initial condition here. And the red solution, what it does, you see it wiggles around a little bit and then it just converges to the origin exponentially fast. And that's the one, I think that was alpha equal 10 somehow with these parameters. Whereas if I make the noise stronger, so that's the blue trajectory. So the blue trajectory is exactly the same parameters, except for stronger forcing. And actually, it's also the same realization of the noise. And so you see that at the beginning, it also wiggles around. It wiggles around sort of in the same way as the red one, just stronger. So it starts off like that. But then you see it sort of goes towards the origin, but then it goes away again. And you see it does these. So what happens is it always exits the origin either in this direction or in this direction. So here I look at it from above. So I only look at the XY component, and the vertical axis is somehow the Z component that points out of the board. What you see is that the trajectory spends most of its time near the origin, but then occasionally it exits small neighborhood of the origin. It always exits sort of in this direction here, more or less. And so it exits in this direction, and then it does a motion which looks a little bit like what you see on the Lorenz attractor, and then it sort of spirals in like that. So it spirals in, and then it waits for a while, and then it exits again like that, and then it spirals in, it waits for a while, sometimes it exits this way, and then it spirals in, and so on. Right? So that's what it does. And so what we want to do is, well, explain that. Well, actually explaining somehow heuristically why the motion is like that, that's very easy. But what we want to prove is that the origin really becomes unstable if the noise is strong enough. So, okay, so one way of slightly simplifying the analysis here, it's really, it's a silly changes of coordinate. So here I just do an affine change of coordinates. I think it's maybe even a linear change of coordinates. I can turn this into something so that the XY component looks more like a damped harmonic oscillator. Okay, so here that's just a linear change of coordinates. And in these coordinates, what you should think of Z as being frozen. Okay, so forget about the equation for Z. So here you see again, it has sort of this linear part, and then there's a nonlinear term. Forget about the equation for Z, and just look at XY and think of Z as being constant. And then what you see is this looks like a harmonic, like a damped harmonic oscillator, right? So the X should be the position and Y should be velocity. And then here you have a damping, and this is the harmonic oscillator, at least if Z is less than 2. Right? And well, so in particular, for Z between 1 and 2, it's overdamped. For Z less than 1, it's underdamped. And for Z bigger than 2, well, at some point this becomes, well, that becomes negative. So that minus sign gets canceled out. This becomes positive. And so then it's not an oscillator anymore, right? So then it's actually an unstable system. And so you see already here, you see clearly what's going to happen, right? So what's going to happen is that if you're close to on the vertical axis, which is what happens here, right? So if you're close to the origin in this XY picture, which means that you're close to the vertical axis where X and Y are close to 0, and you just look at Z, you can forget about this term. This just performs an Ornstein-Uhlenbeck process. So it's going to oscillate between, if alpha is big, it's going to oscillate between sort of large positive values and large negative values. And then if the value of Z is sufficiently positive, well, actually bigger than 2, then this system becomes linearly unstable. And you can just, it's easy to diagonalize, obviously, it's just a 2-dimensional system. And so you can actually see what the eigenvector that has a positive real part, in which direction it points, and it points exactly in this direction here. Right? And so that's why when Z becomes positive, then the vertical axis here becomes unstable, and you sort of run out in this specific direction. But then at some point, well, it's going to stay unstable for a bit, but then the value of Z sort of keeps on oscillating between positive and negative, so it becomes negative after a while. And when it becomes negative, then you just see a sort of damped harmonic oscillator, well, typically underdamped if it becomes very negative. And the underdamped harmonic oscillator does exactly that kind of motion, right? So this is precisely, right? So just from this very naive kind of analysis, you already, get a good intuition of why this is the picture that you see. But of course, it doesn't quite tell you, which one of the two effects dominates, right? So it's occasionally, it sort of switches between a situation where the origin is unstable and a situation where the origin is stable. And what you would want to know is that, well, it's sort of more often stable or unstable, right? Now, again, if we keep with this sort of separation of timescale heuristic, which is not quite correct, but it's really not far from being correct, then what we would do is we would say, well, ignore this term here, and then pretend that the Z guy simply performs this Ornstein-Uhlenbeck process. And then for every fixed value of Z, look at what is the largest positive real part, or the largest real part for the two eigenvalues of that system, and then just average that out over the invariant measure of that Ornstein-Uhlenbeck process. And if it's positive, then you should be unstable. If it's negative, you should be stable. And so if you diagonalize the harmonic oscillator, you see that the two eigenvalues are given by this expression here. And again, you see that if Z is negative, well, then this becomes imaginary. And so the largest real part is always just -1. Whereas if Z is very positive, well, there is going to be one eigenvalue which is very positive, about square root of Z, and one which is very negative, about minus square root of Z. Okay. And so it's kind of clear then that if you integrate this, well, actually here I should have put just lambda plus, right? So you want the one, I should have put real value. Okay, so here you should put a real part of lambda plus. Okay. So if you integrate this against the invariant measure for the OU process, which is explicit, then, well, you can see that if alpha is very small, then this guy is very concentrated around Z star, then you basically just get lambda plus of Z star. And that's the one that somehow changes sign when rho goes, from either side of 1 to the other side of 1. Okay. And so you kind of see that if alpha is small, then you're going to pick up the same sign. Whereas if alpha is large, then this measure is going to be mostly concentrated on sort of large values of Z, so values of Z of order more or less plus minus alpha. In that case, when Z is about plus alpha, then this guy is about square root of alpha, whereas if Z is about minus alpha, then this is just -1. And so if alpha is big enough, the square root of alpha wins against the -1, and this integral is going to be positive. Right? So that's somehow the heuristic. That tells you that it should, at some point, the stability of this vertical axis should change sign. That heuristic is not quite correct. Okay, so because it becomes more and more correct for large values of alpha, but for any fixed value of alpha, the heuristic is not quite correct, simply because there isn't a good enough separation of timescales. But still, so we want to make use of that heuristic, of course, in our proof. So before I say a few words about how to prove that somehow the vertical axis at some point becomes unstable, I want to just say a few words about the uniqueness of the stationary state, which is away from the vertical axis. Okay, so that's this lemma here, which says that, well, there can be at most one invariant measure that's away from the vertical axis. And how do you prove that? Well, there's kind of a standard criterion which says, well, what you need to show is that your system is hypoelliptic and controllable. So what that means, okay, I'm not really going to go into details. So some of you will, of course, know what hypoellipticity means. Maybe some of you don't. Essentially, to check that it's hypoelliptic really means that the noise propagates to all directions. Yeah. And in order to check that, it's sort of a calculation. It's basically you need to compute the Lie brackets between the noise direction and the vector field that gives you the deterministic part of the dynamic. And if these Lie brackets at some point span all directions at every point, then that means that the noise sort of propagates in all directions. So essentially this hyperellipticity, it's some sort of like a local type of local controllability kind of thing. But it doesn't actually quite imply local controllability, basically because the noise can do anything you want, but the deterministic part doesn't, because time always goes in the positive direction. You never go backwards in time. And so you still need to separately check that the system is controllable, basically meaning that if you take any two little balls in your state space, you can find a realization of the noise so that if you start in one of the ball, after a while you end up in the other one. And the way you do this is you basically just argue that since the noise acts on the Z direction, controlling the noise allows you to completely control what happens in the Z direction. So you can really, in terms of a control system, it really becomes two-dimensional rather than three-dimensional. And then you basically just switch between two values of Z, one of them for which the dynamic is sort of an underdamped harmonic oscillator, so it kind of looks like this, and one for which the dynamic is an overdamped, is unstable, and so when it's unstable, you know, the dynamic sort of course looks like this. And now, if you have any two little balls, say you start, for example, this one and this one, and now I want to somehow find a control that brings me from this point to this point here. And so how do I do this? What I do is I take that yellow line, I actually continue it backwards in time. And then what I do is I first start with, I put myself into, well, I make sure that I'm in a situation where I'm not in the stable manifold of the origin for the pink dynamic. So that's already the case. So I adjust Z in such a way that I follow the pink dynamic. And then the pink dynamic is going to do something like this. And so what I do is I follow it sufficiently long so that I end up intersecting, you know, this backward trajectory for the other dynamic starting from that point. And I will necessarily intersect that at some point, right? Because that guy kind of spirals around, whereas here I'm essentially just moving out more or less in a straight line. And so I follow this dynamic until I hit this point here, and now I switch to the yellow one. And then if I wait for a bit, I'm going to automatically just end up at that point, right? So controllability here, it's a very ad hoc argument, but it's very easy. So that tells me I can apply that criteria. That tells me that if there is a steady state away from the vertical axis, then it necessarily has to be unique. So you cannot have like two different steady states that are away from the vertical axis. But now we want to actually really study the stability of that axis. And again, a convenient thing to do here is to do another change of variables to essentially put yourself in polar coordinates. So the correct way of putting yourself in polar coordinates here turns out to be this, which you can sort of see from the explicit solution of the damped harmonic oscillator. And so if you make this change of coordinates, then what you find is the following, right? So if Z is equal to 0, then this drops and this drops, and you essentially just get theta dot equal 1 and R dot equal -1. Okay, and so that corresponds to sort of the spiral, spiraling in. And well, of course, if Z is non-zero, then you get these additional sort of extra terms here. Now, what you can do here, I've neglected, so this dot 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 is the nonlinear terms in the right-hand side for z, which are some quadratic expression in x and y, which is not very important for the argument here. Right? So I just view this as essentially a perturbation, but the equation is still nonlinear, right? So even because in the xy dynamic, I have a term which is bilinear in y in x and z. So now what I do is so the point here is that if I ignore this term, then the theta z system essentially decouples from the r system, right? So the r depends on theta and z, but theta and z don't depend on r anymore. Of course, in reality, they do, because this term here depends on r, but if I neglect this term, then they don't. And then you can make a more precise version of the heuristic that I gave you earlier. And the more precise version of that heuristic is to say, I look at this joint system, so for z and theta, and now this is a system on the cylinder, so it's sort of on the circle for theta and on r for z, so it's a system on the cylinder, which has nice coercive properties because of the minus z term here. And so it's going to have an invariant measure itself. It's not difficult to show that it's unique. And so I give it a name that's called mu alpha. And now what I do is I look at the average of the right-hand side for r under mu alpha, right? And then now that should be essentially the average rate at which the system sort of either approaches or goes away from the vertical axis if it is very close to it. Because if it's very close to it, then this term is essentially negligible. Okay, and so you have this proposition, which is not too difficult to show, which is that, well, if you do this calculation, then if the average of the right-hand side here is negative, then the vertical axis is unstable. If it's positive, then it's unstable. Okay, so that's not surprising. What makes the analysis then tricky, now what we want to show is that if alpha is large enough, then V alpha is bigger than 2. Right? So we want to show that the average of the right-hand side here can be made positive by making alpha large. And so here the theorem is that indeed when alpha is large, then actually this V alpha behaves like some constant times square root of alpha, which kind of goes well with the sort of simplified heuristic that I showed you earlier. And we can prove there's an error of order alpha to the 1/3, but this is an upper bound. It's not expected to be sharp. And for alpha very small, we show that, well, you just converge to the thing that you expect. So this here, if you divide this by 2 and add it to -1, here you just recognize again the real part of the larger real part of the 2 eigenvalues for the linearized system. Okay, and again, we have an error bound. So why is this not completely trivial? Well, the reason is that if you look at this system here, then even though, you know, Z itself again sort of decouples, right? So the whole thing has some kind of triangular structure. If I ignore these terms, then the equation for Z is completely autonomous. And then theta in a way depends only on Z, and then R depends on both Z and theta, right? So you have a kind of triangular structure. But if I look at that pair, even though I know exactly what the invariant measure for this guy is, because that's a Gaussian, I don't know what the invariant measure for that pair is. Right? And this is not a gradient system. It doesn't have any sort of nice structure. And so the only thing I know about it is that the invariant measure is such that if I project onto the Z component, I get the Gaussian with, you know, some variance and some mean that I can compute. But then I have to average this value against that invariant measure. And well, if instead of having a sine 2 theta here, I just had a constant or something, well, that wouldn't really work either, right? So what happens is that you don't have very good control on how theta behaves as a function of z when you're in the invariant measure for that pair. Right? And what you see here is that what you would want to know is that if z is very large, then theta tends to be somewhere, or sort of spend time in regions such that the average of that guy ends up being something positive. Actually, what you end up with is that the average of this guy is going to be about square root of z. So it's not going to be of order z, it's going to be of order square root of z. So this averages out to something small, but not that small. Whereas if z is very negative, then you want to show that this whole thing averages out to something which is order 1. Right? Because that's basically what you, well, that's sort of what we end up proving here. Okay? It doesn't quite need to be order 1, it just needs to be ordered sort of z to the 1/3, bounded by z to the 1/3. Okay, so you have to show that in the invariant measure, so you have to have some kind of control of what the conditional invariant measure for theta looks like when z is fixed. But the problem is that's of course not the same as just fixing z and then looking at what is the invariant measure for that system, right? Because both of them move on the same time scale. Yeah, and so that's what makes the problem a bit tricky. So since I still have 10 minutes, I want to maybe I want to show you a little bit how the proof of the second part of the theorem goes. Okay, so let's assume that we can prove this. This uses kind of a trick that we introduced with Jonathan a few years ago. But so for the second part here, what you do is you use the following trick: is you lift the dynamic to a Markov chain on some space of trajectories, some space of pieces of trajectories. So a space of pieces of trajectories. And the way you do this is you say, well, whenever I start from an initial condition, right? So that's a sort of x naught, y naught, z naught. And now I let the dynamic run, and I run until some stopping time. And the way I'm going to choose this stopping time here is going to be basically the first time at which z is bigger than, say, twice z naught, or z is smaller than z naught over 2. And then there's some exception if z naught is, so this is really only important for z large. So if z is, say if z naught is less than 1, then, so this is, say, and z naught bigger than 1. Okay, so if z naught is less than 1, then I just wait until z is bigger than 2 in absolute value. Okay, so now what happens is and then I restart. Right, so then again, I get a second piece of trajectory, and I wait again until, so now here, that's the first time at which the z is smaller, well, exactly the same thing, but with z naught replaced by z1, where z1 is sort of the value that it takes here. Okay, and so in that way, I take the dynamic on R3, so I have a Markov process on R3. I can turn it into a Markov chain on some, very large space, which is the space of pieces of trajectory. Right? So the transition probability, so the initial condition now is a piece of trajectory. And the way the transition probabilities go is I simply look at the last value of my piece of trajectory. And then I take this as an initial condition for my equation. I solve it until first time this condition is satisfied, and that gives me a new piece of trajectory. Okay, and so I can view this as a Markov chain on pieces of trajectory. And if I have any function f that goes, say, from R3 to R, so I have any observable of the original system, then, so say if I call that space E, then I can lift this into a function f hat that goes from E to R by simply integrating along my trajectory, right? So say U, so if I call U my trajectory, I turn this into just the integral from 0 to, say, tau of U, which is sort of the length of the trajectory of f of U of S ds. Okay, so I simply integrate my observable along that piece of trajectory. And so what's the point of this construction here? So the point of this construction is the following. So first one knows, or one can show, so this is not very difficult to show, that if f is, sufficiently nice, so you need some kind of, integrability condition, that if I integrate f, the integral of f against the invariant measure of, now, so what I do here is I ignore this. So I look at this reduced system, and I furthermore even ignore the R, right? So I really just look at that pair theta z. And now I take an arbitrary observable and I look at the average of the observable against this invariant measure mu alpha. Then the claim is that this is equal to the integral of f hat of, say, capital U against mu alpha hat d capital U, where mu alpha hat now is the invariant measure for this Markov chain. Okay, so that one has an invariant measure, which I call mu hat. And so what you do is you take this and you divide by the average length of these trajectories. So in this way, we relate the invariant measure for the original dynamic, or even for this kind of linearized, half linearized dynamic, to the invariant measure of the corresponding Markov chain on a space of excursions. And this formula is true, basically, whatever the stopping rule is here. Okay, so at least the stopping rule needs to be, it shouldn't be too crazy, right? I mean, you need to make sure that you stop after a reasonable time and that like the pieces don't end up getting way too short or way too long, right? But if the pieces are all of sort of reasonable size, which is the case here, then you have this identity. And the reason why this identity is useful to us is that this allows us to actually exploit dynamical information much more effectively in order to say things about this invariant measure. Remember, I told you that the problem in showing this is that we don't know what the invariant measure for this system looks like, right? We don't have an explicit formula or anything. And so we cannot just, integrate this function against the invariant measure. So we want to have some kind of information about that invariant measure. We want to know where it concentrates also. But it's difficult to extract sort of, pointwise information like that. But at the end of the day, we're really just interested in the average of one specific function, which is this z times sine 2 theta. And so now what this tells us is that actually we can control the average of that function against the invariant measure that we're interested in. We can get a lot of information out of that if we know how it averages along pieces of trajectories of that type. Okay. And so then the idea is that, well, for that function, so for f of u is equal to, well, it's basically z over 2. So what was it? Z sine 2 theta, sorry. Right, so for this function, z sine 2 theta, if I look at the average of f hat along some of us ds, along some piece of trajectory of this type, where I use the stopping rule, then these pieces of trajectory are sufficiently long so that this average is actually very well approximated by the average of the function, I think, 2 square root of z of s ds. Okay. And so here there's an error, which you can control. And so once you know that this is the case, then you're basically done, right? Because then what you know is that this quantity here, well, you know that it's equal to that. But then here I rewrite this. I sort of, since this is invariant, I can put here in between one round of the transition probabilities of this Markov chain. And then the integral against the transition probabilities of this function is well approximated by the integral against the transition probabilities of this function. And then I can go back and I kind of conclude from this that the integral of z sine 2 theta, oh, sorry, and here there's actually, so I forgot. So this is only true for positive z. So this is true for z is positive. And so then what this tells me is that the integral of this function against mu alpha is actually very well approximated by the integral of square root of z, indicator function z positive, against mu alpha. And now I still don't know what mu alpha is. But here, now the function that I'm integrating is a function that depends only on z. And I know what the marginal on z is, right? Because the z dynamic does not depend on theta, and here it's just an OU, so I know it's completely explicit. It's a Gaussian measure of known mean and variance, right? And so this here, this quantity is known. And so in this way, right, so using that trick, you see I can use sort of like averaging principle on these pieces of trajectory in order to replace this by that, which then allows me to obtain information about the invariant measure without actually having to know what the invariant measure looks like. Okay, and so that's sort of the main point. So of course, then one need to actually show that this approximation is valid, and a big chunk of the paper is sort of the fiddly bits about showing that this approximation is really valid in the various regimes that you have to consider. I think I stop here, and well, thank you very much for your attention.
Thanks a lot, Martin. I think there's already one question right in the chat.
Oh yeah.
You have numerics confirming similar behavior for 2D Navier-Stokes.
Right. No, so we haven't actually done the numerics. I mean, I think you probably wouldn't expect to always have a behavior like this, but you'd probably expect it if, well, at least if the noise has the right kind of shape in some sense, right? So of course, in the case of Navier-Stokes, now your noise also has spatial dependence, and then you would have to choose maybe the spatial dependence in a smart way. But we don't, no, so we haven't actually done any numerics for Navier-Stokes. You would probably expect it more in the 3-dimensional case, right? Yes.
Other questions?
Is that, I see someone raising his hand. Is that Edris?
Oh, you can unmute your microphone if you want to.
Yes.
ask.
Hi, everyone. Hi, Martin.
Hi.
So remind me, I mean, at the very beginning, you mentioned that eventually you can see there is like two ergodic components, or at least two ergodic components.
No, in the end, we show that for alpha large enough, there are exactly two.
Aha.
Right, because we have this, so let me see, right? So here we have this uniqueness. So we have this at most one, there's at most one which is not on the vertical axis, and there's always that Gaussian measure that lives on the vertical axis. So there's always either one or two. And we show that for small alpha, there's one, for large alpha, there's two.
I see. I mean, of course, I'm not a stochastic person. In the deterministic case, there is some kind of like theorem about dissipative system, Lorenz is included, that usually the set of steady states is generic finite, and when it's finite, the number of such states is odd number. And I was wondering if one can show similar kind of like results, but you're telling me there is exactly two, so such a result maybe not available the minute you put stochasticity.
Yes, so here, I mean, the thing is that you see, when you add noise, it tends to really, I mean, generically, you tend to just have one steady state, right? So if your noise is anywhere, you know, near sufficiently non-degenerate, then it's going to smoothen everything out, and so you're going to just have one. And the reason here is that we added noise precisely in that way, that you have the, right, there's this invariance of this vertical axis, and we make it point precisely in that direction to enforce that line to be invariant, and so that's why we can end up with two steady states somehow. But if you just put, you know, some noise in some kind of random direction, generically you would expect the number of steady states to immediately go down to one.
One, yeah. Yeah, one is an odd number because, as I said, the generic
one is an odd number. Yeah.
Yeah. You see, generically, that's exactly the result. Generically, for generic forces, that the number is finite and it is an odd number. And this is just an argument from degree theory, sort of like, you know, it's not like because you look steady states of elliptic problem or some kind of like elliptic problem, so we can show such results. In any case, I was just wondering. Thank you very much for a nice talk.
Yeah, thanks.
Other questions? I have one concerning the critical value of alpha. Where does the critical value comes in which estimate? In the talk, you always speak about small alpha and large alpha, but then you said that there's indeed a critical value of alpha.
Well, so we don't have a formula for the critical value, right? So there's, I mean, this proposition tells you that, well, the critical value of alpha is the value for which V alpha is 2. But V alpha is defined very indirectly because it's defined as this integral against this invariant measure, and you don't have any explicit formula for this invariant measure except that you know that it exists. And then what we show is we simply show that, you know, this guy depends continuously on alpha, and we know what's the asymptotic for large ones, we know what's the asymptotic for small ones. And so, you know, if there's one asymptotic which is sort of bigger than 2, the other one smaller than 2, so somewhere in between there has to be a critical value where it's 2. But for example, we don't know, right? We don't actually even have a monotonicity result. So it could kind of cross the value 2 several times. So we certainly don't expect that, but we cannot actually rule that out. But if you do, you know, you can use that heuristic. So there's the sort of naive heuristic, which would be that, well, the critical value is the one for which this quantity is 0. And this quantity is some sort of approximation of the actual real quantity that you should consider. But that one, we did some numerical simulation. So in this example, for that numerical simulation, we did actually play around with the values of alpha to try to figure out what is the critical value, just sort of numerically by section. And on the other hand, we also computed the value for which this crosses the threshold. And we can see that they are actually very close. So in the sense that so that tells you that this heuristic, even though it's wrong, it's kind of very good. So in this particular example, I think the real critical value of alpha was something like 27.8 or something. And the critical value that came out of that heuristic was maybe 27.2 or something along these lines. So the two values were really close to each other. But somehow the numeric was sufficiently precise to see that they're actually not the same.
Other questions? If not, I have another one, if I can wait.
Sure.
The zeta axis is special in the Lorenz system in the sense that when it's fully chaotic, you have this sort of like 1D tent map dynamics for the local maxima of the zeta component. Okay. So if you take the zeta component and then in the fully chaotic case, you study the discrete map joining from one local maxima to the other, you can show that this is a sort of like a tent map.
Okay.
Is there something similar then in this case when you add noise, then for the local maxima of zeta there is some special dynamics or not? Just a curiosity.
Yeah, I don't know. It's kind of difficult. It's a bit difficult to define what you actually even really mean by local maxima, right? Because the Z component here is sort of going to look like a Brownian motion. And so it has too many local. Of course, I sort of see what you mean, right? Because you see that. I mean, here I didn't draw the Z component, right? So the here the X and Y components look quite smooth. The Z component looks much more like like that. So now, of course, when you look at it, I mean, it has sort of features that are a bit similar. I mean, obviously, it's going to more or less look like the deterministic dynamic with some kind of noise superimposed. But yeah, no. So I'm not sure. I don't think I have anything intelligent to say about your question.
Or the local maxima where when X and Y cross the vertical axis, so that and they go to 0 or they change sign. Okay, then you. So there are no other questions. I think we can thank the speaker again.